Hey guys, how are you doing? I don't really know why I ask that every time because you can't exactly respond, but whatever. Today we're doing Kickstart, and this is my first, no, I guess my second time doing this. I'm recording, first time making a screencast of it. But it should be fun. It's kind of early, but should still be fine. I'm gonna, as always, add the subscriber count. As soon as I figure out what's going on with my files. And as always, if you're new, I always add the subscriber count to my template, and then the ultimate goal is for us to get a memory limit exceeded verdict on these submissions because of this. So, it's probably never going to happen, but it's worth a shot. How do I get into this? I actually haven't joined one of these rounds before. So like an open button. / will the pages load. Cool. Well, it's loading again. Don't really know what's happening. Is it loading the round, I guess? And then, oh, nice. That's fun. I guess it's loading the round. How do I like actually get into it? Oh, there it is. Okay. Alright, we can open everything and get started. Kick_start. Kicks off each day for starting. That's perfect. So starts with the string kick, ends with the string start, and the overall fragment makes little sense. So kick and start don't share any characters, which means that it should be chill, I guess. Okay, so first what we can do is we can let's just do the thing, case number, and we can read in the string. And basically the idea is we're going to find all the positions of kick and all the positions of start, and then we can find for each position of kick how many starts there are after. And that works because kick and start don't share any characters, so it's like not a big deal. How to do this? How to do this like not annoyingly? Okay, so basically, if s.substring starting at I and then of length 4 is equal to kick, then add that position into what we're doing. And then the same thing for, wait, it's I plus 3, right? Normally we would do I, then we need to extend by 3 characters. And so the position m minus 3 would be valid. No, it would not be valid. We want 0 indexing. So n minus 4, n minus 1, okay. And then we just do the same thing. If this is equal to start, I'm using a deck here so we can easily do this. So then essentially we're keeping a like something like this. Say the positions are like this, even though it doesn't really make sense in the problem's context. 2, 6, and like 9 or something. then once we're here, all of these 3 positions work. But once we get here, once we get to the 3, this 2 doesn't work, so now we get rid of it. Once we get here, this 5 works for these 2. Once we get here, this 7 doesn't work, and so 6 is less than 7 and we get rid of it. This works because everything's sorted, so we can just like remove them in order when we need to. And then we just add the size of the deck. Cool. What's with that? We're reading in test cases. Okay. Oh wait. Don't have a thing. 305. Okay, looks right. We didn't screw anything up. We're iterating to the end of the string. We do the deck. It works. I hope. And we select C++. Okay. Let's go for the next one. You have a square matrix n by n. Oh, that's a short statement. Nice. Top left, number of coins can only go to I plus 1, j plus 1, or I minus 1, j minus 1. Okay, we got A. So we can go to, we can go only on the diagonals. Okay, so this is the idea. Basically, you can only be on the diagonal that you're on. So for example, if you're here, then, like say this 3 by 3 grid, if you start here, you can only visit this. If you start here, you can only visit this. If you start here, only this. Here, only this. And here you can visit these 2, because you can visit only the diagonals that you're on. So basically, we just like group together all the diagonals, and then we figure it out from there. So this is essentially, I think a diagonal can be represented as I minus j. Like for example, this, say we write out the rows like this, and this. Then these are all going to have 0, 1 minus 1. This is going to have 1, 1 minus 0, 2 minus 1. This is going to have 2, this is going to have negative 1, and this is going to have negative 2. So we can just add n to these, and then it'll work as we want. Or add m minus 1, I guess. C into n. What the hell? I screwed my own formatting. Okay, so basically now we do I minus j plus n minus 1. And that works because the lowest j can be is n minus 1, plus equals x, and then we have to actually read in x. And we can just kind of like keep the answer as we go along. Nope. And 2n is big enough, right? Because the biggest I can be is also n minus 1. Yeah. So then this should be 14 and 9, I think. 14 and 9. Yep, we're doing the diagonals right. 1, 6, and 7. Everything is within bounds. 2 times n is big enough. Okay, cool. Sorry. It says 3 subtasks. Okay, we got that one. How are we doing right now? Seems like everyone has got the speed. Okay. Combination lock has W wheels. 57. Alright. I gotta be faster on the later ones then. Combination lock has W wheels. Fun. Each moment, each wheel says a specific value on it. You can change it to x1, x plus 1, x minus 1, wrapping around between 1 and n. The wheel currently shows the value 1. In one move, you can change its value to 2 or n. Okay, well this is kind of a slope thing, where you can solve it by analyzing some function of how each of the distances changes, and I think therefore it's got to be that the answer is on some point. So we only have to try all the possible values and see how that works. Basically, like imagine the total cost as a function of, like it's the sum of a bunch of distances. It's like either you. There are three like things. Each thing is say you have a lock starting in position X and you want it to become position Y, then this is kind of like the minimum of just going directly. You can go up by n, and then you can go you can underflow and go down and then like become higher up, or you can do the same thing for below. So the function kind of looks like this, but like there are only certain points where this is going to be decreasing. Okay, this seems annoying though. Actually, maybe it's not necessarily a point, but there's like some stuff going on here that makes it easier. Let's sort the values because why not? Doesn't matter the positions of the wheels, so we can sort them, I guess. Cn to n and k. And then what's happening here? Just test set 1 is simple. Test set 2, test set 3 are weirder. At least this isn't heuristic brute force though. That's nice. I like that. So somebody have to try this stuff efficiently. Okay. So T is 100. Alright, they just have big data. So somehow we do this efficiently, I guess. Which is annoying. So I guess this function is kind of workable. Let's say we let's say we like figured out what this function looks like, kind of. Like for some values of y, maybe it looks like something like this. Then these 4 points are the only points we really care about, and then between these we have a starting point and a slope. So for example, this will start here and then it'll go down here, and then this will start here and then it'll go down here. And if we kind of, I think, like if we take the functions of all of these and then we kind of add them all together, then the minimum value on the final function that we get from adding all these together is what we actually want. Yeah, so that's kind of cool because each point is going to have like each individual function is going to have a small number of interesting points. So the overall function should have only O of n interesting points, even though they're 10 to the 9th values. And therefore, we just need to figure out like at what point each of these become optimal. Which in itself is annoying, so I'm not sure what to make of this. Now you can find the point where each of these become optimal, kind of. I guess this is going to dominate the function for some range, this is going to dominate for some range, and this is going to dominate for some range, possibly circular ranges, which is quite weird. But like only for certain things, I guess. Yeah. Okay, let's see. So for each thing, I don't think we actually need to sort this, but whatever. So basically I'm going to store the function like this. You have a bunch of starting points like 7, and then maybe the slope is -3 or something. And then basically by summing up all of these points, we can get like the addition of the overall function if we sum up the points and slopes of everything. And then we can kind of like do a sweep line, and the next interesting point we have the sum of slopes, so we can figure out exactly how much this has changed because we know the slope. And then we can recompute the new slope over here and then just keep going. And then at every point we can take the minimum and have that be the answer, I think. But to do that, we just need to do the function. Just don't really do anything. Okay, let's think about this more carefully. So we have a wrap value of 10 and we have a value of 7. No, those are too big. Let's do something I can draw. 7 and maybe 6. Then we have these 7. And this is over here. And then maybe we want to convert it to 4. Actually, let's just consider everything. Here, the best thing to do is to go around. Here, the best thing to do is to 1, 2, 3, go around. Here, the best thing is to go this way, so I'll draw these points green. Here this way, and here this way. So there's this kind of boundary point between them where yeah, there's this boundary point where stuff gets interesting. So up to here, from 1 and 2, the function is defined as, so this distance is 1, 2, 2, wait, different color. Why not? So this is 2, this is 3, this is also 3, this is 2, this is 1, this is 0, this is 1. So there are 3 different breakpoints, kind of. This point where the slope is increasing, this point where the slope is decreasing, and this point where the slope becomes increasing again. And if we had more points to the right, then this would just still be increasing. So this could be represented as a point 2, and the slope is positive 1. This could be represented as 3, and the slope is negative 1. And this can be 1, and the slope is positive 1. Okay. So how do we figure this out? So one slope breakpoint is the point itself, and then I guess it's not possible to have. I don't think it's possible to have it for some specific position for the orange point. It's not possible for there to both be a position where it's optimal to wrap this way, and a different position where it's optimal to wrap this way. I don't think that can be the case because this is just. It's either on one end or close to one end, in which case you don't need to wrap, or it's in the middle, and in which case you probably don't need to wrap either way. It's kind of weird like that. But that does make things easier, I think. Okay, so what's the exact position of this? By the way, we can kind of cancel out this function by adding another point here. This is essentially, this function would be 4 over here. So here we would add a point 4 and then cancel out the slope by doing negative 1. Yeah. Let's do a map, actually. I think that makes it easier, because then we can just kind of add these points. We could do a separate one for value and slope. Slope. So now we just have to figure this out, and that is not fun. So okay, let's compute the left boundary, I guess. When does this happen? So it's the coordinate where x minus y is equal to x, what is it? Plus n minus y? No. Yes. Yeah, it's kind of like shifting this coordinate over by n, and then just going right until you get to the 0. So it would be x plus n minus y. We can drop the absolutes because we know for this to be possible, y has to be greater than x. So therefore this is y minus x is equal to, and x plus n is greater than y, minus y. So this is 2y equals 2x plus n. What does that make this? We're interested in x, so we do x equals y minus n over 2. And therefore, if n is odd, then it's a fraction, which is annoying, but n is odd. How does this work? And then if we're interested in the minus, it's just the same thing but plus n over 2. Okay, so assuming this is y, the point of interest we have is y minus n over 2. And assuming the other one, we have x equals y plus n over 2. So therefore, these are going to be these points of interest, I think. And if it's odd, then it's like kind of more annoying, but I think we can... If it's odd, we can do it like floor, and then therefore it'll be to the right of this point, say here. And if it's even, then it doesn't matter. And if it's odd here, then we'll also do, or we can do ceiling here, and then it would be to the right of this point. Sure, okay. So the way we can do this kind of is we can keep a set of like the points of interest, that is the starting and ending points of the function, and then I think that just kind of makes everything easier. Yeah, it should. Okay. So we automatically start with 0 points dot insert n or k. Yeah, k. Sorry, all of these should be k, not n. N is the number of wheels we have, but k is what we're actually interested in. Then we can do left equals, I think left is reserved, so let's not do that. So this is ai minus n over 2, by default floor, if lval is within the range. Insert that. Then plus ceiling is the same as ceiling. And if it's within the range, points dot insert. N is kind of special, isn't it? I feel like this doesn't work because the ranges can be like weird. Maybe it's not so smooth, I think. That could actually be possible. What the hell is going on here? Maybe it has to do with like n being even. N is even, this works out. If n is even, this is simple, because all the points are going to be integers. The problem is actually that I'm doing this to get the slope. But the problem is that like these are the same, and what I need is for this to be 4, which isn't gonna work. So maybe what we do is we Yeah, and then we kind of do the same thing, I think. Because then we'll treat both this and this as points, and that should work out. It's gonna have a mega constant. Whatever. And we'll make a vector because that's easier. Give it a bunch of space because it doesn't matter. Point.pushback x, okay. And then now we kind of just do this. For should be I plus 1. And we just compute this function. So this is point I minus AI, abs, point I plus n, k minus AI, abs, point I minus k minus AI. Because we can either go from above, from below, or normally. Come on. This bracket just means you can do all three at once. Wait, it shouldn't be AI. Shoot, this should be like J. Yeah. Because otherwise we have two I's. Then we can duplicate this and kind of just do the same thing, I guess. So this is point J plus 1. We're comparing the difference. F2 minus F1 over point J plus 1 minus point J. This is both of these are integers, and the result should be an integer, so that should be fine. Then val let's see. So val point J plus equals F1. That's the value of the function. Then slope. Let's call this slop. Slope point J plus equals slope, and then we kind of have to like undo that. So val point J plus 1. How's this gonna work? I guess it's should be point J plus 1 is equal to, we subtract F2 plus slope because we're going slightly beyond, so we need to extend the line a little bit, and therefore we need to add one more unit of slope. And then slope point J plus 1 minus equals slope. Alright, and then once we do that, we just kind of like keep going. For ants equals, what do we make it? 10 to the 18th. 2018. Wait, why do we need to do this? I think I can just get away with not having this be a thing. We can just do this here. I don't actually know why I did this. We can just we don't need to extend this line. We can kind of just subtract this here, and then this new function will take over. Is that how that works? I think so. Yeah, it should. Okay. So slope point J plus 1. Okay. per plus equals the second of the pair, and then our slope plus equals this will just give us the first position. So what we want to do is, once we have this function, when we like move from here to here, we need to compute how much this has changed, and therefore we can just like use the slopes. Yeah. So let's see, plus equals x dot first minus last times our slope, and then yeah, and then this is our slope plus equals slope x dot first. It should be the minimum. Okay, no way this works first try. So let's go over it. We print the case number. That's a good idea. We read in the two integers, and once we do that, we read into AI. Take two maps for value and slope. Take the points. So we begin with 0 and k. Even though k isn't in the range, I'm using it to just kind of like be convenient. Actually, I don't think we even need to do that. We can just do k minus 1. So that's cool. Then the first is minus floor number 2, which is the right point of whatever this is. And then we insert that and that minus 1. Then we do plus the ceiling of n number 2, which is the right point of whatever is going to be on the right. And then we just kind of go for it. Then we then we create a vector, and then we kind of like we create these points, these like different things. So the first is the minimum of going directly, going above, going below. And maybe those are out of order. Yeah, this is going below, this is going above, whatever. And this is the same for the other point. It's just the function itself. The slope, we can just assume it's the slope between those two. And then and because we don't divide by 0 here because all these values are unique, and then we increment it on one end and we decrement it on the other end to show that this value no longer matters. Let me just kind of continue. For each thing, we apply the slope to it. X dot first, which is this, b, and then a, and then the answer is b minus a times m, where m is the slope, because it'll just like go down that much. And then we add the new function values, like the changed ones, to this, and we update the slope, and everything works out. I hope it works out, maybe. Does it even compile? It does compile. Wow. That's kind of nice. That is not good. Where are we right now? Okay, let's just that's really weird. What's happening here? Okay, so like all the slopes are negative for some reason. Why? Are these values all positive? Well, yes, it's absolute values, of course. So we have 0, 1, 2, 3, 4. Fine. The concern is that all these slopes are negative for some reason. Don't actually know why. Some of these should be increasing, right? let's just we commented out the sort, so everything will make sense. Okay, what? So 0 is 0, 1, and 4. 0, 1, and 4. That would make sense. Wait, what I should do is decrement this, otherwise it would be between 1 and n, or wait, how does this work? Yeah, it should be, I want it to be 0 index because that's more convenient. -3, -8, okay, slightly better. Not that much better, but slightly. I don't know what's up with that. Okay, so 0, 2, and 4. That is sensical. Is it? So it's 1. Wait, the point should be... Why is it not... Oh, I didn't even put in the actual... Okay, yeah. Yeah, it should definitely... AI should definitely be one of the points. Whoops. Because that's the point where it, like, stops... That's worse. Because that's the point where this, like, stops going up and then starts going... Or it starts going down and then starts going up again. Okay, so 0, 1, 2, 4. This just goes in too fast. Oh, and then I forgot to update last. Yeah, that makes sense. God, okay. Why? So it, like, gets very, very close, and then something just stops working. What I don't understand is why everything cancels out except for, like, this part. Oh wait, okay, this should not be k plus. This should not be k minus 1, actually. This should be k. Yeah, we kind of don't want this whole thing to cancel out, I think. The problem is that we're canceling all these functions out right at the end, but we don't want to do that. Because there are no more functions to, like, have. So let's say, if x dot first is not equal to k minus 1, then we can do that. What? Oh, I didn't. 2 and 3. Better, but not good. And we're doing the function wrong anyway. So somehow this is, like, very bad. Why do we have a 1 here? Part doesn't make sense either. We shouldn't have a 1 here. We definitely shouldn't have all numbers here. Kind of confused as to what's going on. Very confused. Maybe we should have all numbers, actually. I'm not entirely sure. Maybe? Ah, this problem, man. So we have 0. And at 0... okay, let's just, like, do this. Like, what is going on here? So here we have 0, 1, 1, 0. That is correct. Then we have 1, 2, 0, 1. That's also correct. What does it think n over 2 is? Oh, wait. Oh, it should be k. It should be k. Should be k once again. Oh boy. Anything else stupid where we didn't even like use the right value? K. These should be k2. This is just like control Fn. N to k, n, fine. Okay. Everything else is k, right? Let's just fix our stupidity. 2 and 8. Alright, let's see. Is everything right? So we have 5, 3, 2, 3, 5. That just makes sense. Yeah, that's what it says. 5, 3, 3, and 5, and 2. So 1, 2, 9, or 10 all have 8. Yep, okay. And then the rest just kind of have more. Let's get rid of the debug. Okay. This is a fun problem. And this seems even more fun. Oh boy. You have a game with n cards laid out in a row. The ith card has the integer AI written on it. The game is played in n-1 rounds. During each round, Ponko will pick an adjacent pair of cards and merge them. Suppose that the cards have the integers x and y written on them. To merge two cards, he creates a new card with x plus y written on it. Then removes the two original cards and places the new card in their old position. Then he receives x plus y points for the merge. During each round, he will pick a pair of adjacent cards uniformly at random amongst the set of all available adjacent pairs. Cool, we got this. Okay, thank God, honestly. I would be very annoyed. Was this easier? Maybe it was easier than I thought. How are people doing this so fast? Maybe they just like didn't have problems or something. Or they maybe might have done it easier. Here we are. I don't know how people did that so fast. Interesting. Alright, so my idea for this is contribution to the sum. That is, for each card, how many times will x contribute to the answer? So we have like 1, 2, 3, 4, 5. How many times is this card, specifically this card, going to be part of a merge? So on the first turn, it has a, there are 4 possible merges to do, and 2 of them use this. So there's a 2/4 chance of including this one in the merge. And then once we do, we have 3 cards left, or we have 4 cards left, so then there's a 2/3. Unless we merge this one on the right, in which case we have a 1/3 chance now, because we only have 3 possible merges, these. So this is contribution to the sum because we consider each element individually and then figure out how much it contributes. And therefore all we need to do is like figure out how much it contributes. And the way to do that is, I don't know. Isn't that great? Yeah, it is. Okay. Well, alright, so like, at a certain point, it might run out of stuff on the left. At a certain point, it also might run out of stuff on the right. And when either of those happen, we lose a possible merge, and so we go from 2 over x to 1 over x. And then when we like lose both, then we go from then we get 0 over x. 0 over x. So what's n? Is n small? N is 5,000. Okay. We can kind of unmerge things. One thing is DP. Let's see. So what if we do something like this? Let DP of A and B be the probability of having A on left. Like, so we're here. We have A numbers on the left and A numbers on the right. So when we have one number left, it's DP of 0 and 0, and then we kind of go backwards. So the transition is either we get a number on the left or we get a number on the right. And the question is, when does that happen? So for DP of A and B, we have A plus B plus 1 numbers. For example, say we're here, we have 1 on the left, 3 on the right, so we have 5 numbers because we include this one. Then what's the probability that last turn we made this merge? Well, it's just like, it's the probability of there like being a number here. How does that work? What's the probability that we made this merge last time? It's kind of like a backwards recurrence. It's kind of weird. Maybe it's I think it's more like, what's the expected number of merges? Yeah, okay, this shouldn't actually be probability. It should be more like some math stuff, like the expected number of merges we had with the number that we're interested in. And so therefore, the probability of us making this merge or this merge would be like weird. But that's kind of not what we're interested in. What we're interested in is like the probability for a specific L and R, right? So how do we do this backwards, where we start from 0, 0, and then we end up to some A and B? Well, either we did this merge, or we did some other one. And so what does that mean? Or maybe we don't even need to do that. What we can instead do is not even go backwards and just say that, like, say we're here. Then either we merge this or we merge this. And then we're interested in the expected number of moves where we have 0 on the left and 3 on the right, or the expected number of moves where we have, say we merge this, then we have 1 on the left and 2 on the right. So dp of, or we merge something else, in which case we have, yeah. So dp of A and B is equal to, let's say we have, yeah, so it's 1 over A plus B, because that's the probability of making any specific merge, times dp of A minus 1 B, if A is greater than 0, plus 1 over A plus B of making a merge on the right, so dp of A B minus 1, where B is greater than 0, and then A plus B minus 2 the rest, like whatever these possibilities are. So it's kind of like we split this into left and right. And actually these should be plus 1 here and plus 1 here, because otherwise it just wouldn't make sense. So let's just kind of like do that. So let's long double dp. Okay, dp 0, 0 equals 0, obviously, because we can't have any like expected things for that. So then for LLI equals 0, I is less than, C into N. N I plus plus, for LLJ equals 0, J is less than N, J plus plus. Right, okay, so we can have at most N minus 1 on the left and right. So LD tot equals 0. LD this is saying if either of them are greater than 0, otherwise we've already computed it. So next, prob equals 1 over I plus J. Not 1.0. Then if I is greater than 0, tot plus equals prob times 1 plus dp I minus 1 J. Same thing for J. If I is greater than 1, let's see. So it's I minus 1 divided by I plus J times dp I minus 1 J. It's kind of the same thing. J is greater than 1, then it's J minus 1 divided by that, and then I, J minus 1. So what is it? So it's dp of I on the left and n minus I minus 1 on the right. Does that make sense? I think it does. Yeah. Cool. What? Huh? Oh, I didn't even yeah. Ij equals tot. And then cout set to precision 17, or just, I don't know, 10 fixed. Seg fault. Cool. Why? What's happening here? I guess we're not finishing under an hour. That's sad. But we can Still, like, do some stuff, right? Yeah, what's happening? Where do we get to? What? Do we get to this point, or do we just, like, die in the middle of the DP loop? DP loop? Yeah, okay. Where do we get to in the DP loop? Oh, we need to endo. Why do we die here? I is greater than 0. Oh, whoops. Whoops. Copy paste there is stupid. 352, 20. Just make sure that works without debug printing. 20, 352. Okay, looks good. Finished in just over an hour, I think. Okay. To be honest, I kind of hindered myself by like doing out the whole screencast thing and kind of like, you know, I kind of went over the whole solution before I even coded it. So that's fine. It's not really about the rank. But this is still pretty good anyway, so whatever. Good job, TMW and Directo at the same time. Okay, so anyway, let's with 2 hours left, let's get into the solution, and then I will just I guess it'll just be that. Does this link work? This link might work for my submissions, I think. Okay, that should be good actually, because I usually like to share my code at the end of it anyway. Yeah, so with a little bit of time left, a little bit being 2 hours, I'll just go over all the solutions and we'll be done. Okay, so for the task called kick_start, basically the idea is you have a string and you want to find out the number of, let's say for example you have, let's just consider the string kick start. You can hear my mouse going wild. Kick and start. Basically, you want to find the number of substrings, that is, contiguous like subgroups of the string, that both start in kick and end in start, regardless of what's in the middle. You can even have nothing in the middle. For example, this is a valid string. And you want to just find those number of substrings. N is big, 10 to the 5th, so you can't like, just like, you can't brute force stuff. But you don't need to. Notice that kick and start don't have any overlapping characters, which means that any instance of kick is going to be completely separate from any instance of start. So what if we just like listed out the instances of kick and start? Let's say we had something like this. So we have a kick that begins at position 0, a kick that begins at position 4, a kick that begins at position 8, 13. We have a start that begins at 8 and another start that begins at 17. So then, like, any start that's after a kick is just going to... Like, we're interested in the number of instances where there's a kick at some point and then there's a start, like, after it somewhere. So let's just find, for each kick, how many starts there are after it. And then once we do that, we can sum up the value, because the number of starts after this kick is going to be the number of valid substrings where this kick is the beginning. Oh, and I guess kick has overlapping characters with itself, so technically this string is also valid, and this would have the same answer, like kick start. But it doesn't really affect anything because these indices are going to be disjoint anyway. Like they're not going to overlap each other. And then we can find that this one takes these two, and this one takes this. All right, so let's list out these indices in sorted order, and then so for this one we want to find the number of these red values that are after it. You can do this in like literally any way you want. You can do binary search. You can do 2 pointers. I used a deck, which is kind of a smart way to do 2 pointers. Basically, you keep a deck of these values, and then you iterate through these values in sorted order. And then when you're like here, for example, while the current value in the deck is... Did I like... Wait, what did my submission do? Did I even check for the size? Yeah, okay. So while the beginning value in the deck is less than this, which means that the start is before this kick, you can kind of just like remove this from the deck. So when we're at 13, we'll remove this 8. Say there was another value 9, we would also remove that. And then we would get the 17. 17 is once again later than 13, so we'll be good. And then at each stage, you can just add up the size of the deck, which is exactly the number of starts after this value of kick. Okay, one final thing, just be careful about sizes. If the deck is empty, you don't want to access an element that doesn't exist, so just like handle that separately. Yeah, okay, that is the first one. Let me do the second maximum coins. This one I found simpler, and combination lock I found the hardest. I'm not actually sure how people did it so quickly, but this one is fine. So the basic idea is you have a matrix of n by n, and let's say you're here, or let's say you're here. You can either go to cell I minus 1, j minus 1, as in this one, or you can go to cell I plus 1, j plus 1, as in this one. And you, if you visit a cell, you can like pick up some number of coins. If you revisit a cell, you can only get the coins once, so you can't get it again. But basically, you want to figure out the best starting point to give you the maximum number of coins possible. And so the number of coins you get is basically the sum of all coins of the cells you can reach from a certain starting point. Alright, so let me kind of just like draw out all these paths. I'll keep using orange. We'll just take some arbitrary starting points, and then we'll see. So from here we can reach this one, we can reach this one, and we can reach this one. Because we can just go from here. Here we can reach this one, and this one. Here we can reach this one. Here we can reach this one, and that's it. Okay, now let me be more organized and draw these kind of as diagonal lines, right? So starting here, you can reach this entire diagonal of the matrix. Starting here, you can reach this entire diagonal of the matrix. Starting here, you can reach this entire diagonal. Here you can reach this one. Here you can reach this diagonal. Here you can reach this diagonal, and here you can reach this one. Now that's just it, because, I mean, look, from here, you can get every cell in this diagonal, and that's all you can get. So now the problem is just, for over all diagonals, which one has the greatest sum of elements? Because like the diagonal is exactly the set of cells you can reach from some certain starting point. And so now we have to ask, how do we figure that out? So n is like big, which means that, n is big, but not that big, but big because we need to be able to read input, but assume n is big. Like we need some sort of O of n squared algorithm, where n is the size, where n is the number of rows and columns, not the total size of the matrix, right? Yeah, n by n matrix. So from here, essentially what we do is we figure out some way to represent a diagonal. Let's kind of draw out the rows and columns here. So we have 0, 1, 2, and 3. Here we have 0, 1, 2, and 3. Now you can notice that every diagonal has some point on either the first row or the first column. So, like, you can just, that's one way to do it. You can just, like, fix some starting point on either the first row or the first column. Specifically, all of these cells have their own diagonals. And then you can kind of just, like, go through the diagonal. Like, from here, just go until you get the end of the matrix. Just, like, explicitly visit these cells, sum them up, and take the maximum over all of them. A smoother way to do it, in my opinion, is you can represent each cell as the row minus the column. So, for example, here we'll have 0 minus 0. Here we'll have 1 minus 0, 2 minus 0, and 3 minus 0. We can have negative 1 here, 0, 1, and 2, negative 2, negative 1, 0, and 1, and negative 3, negative 2, negative 1, and 0. And notice that these diagonals all have the same value in them. And so therefore we can kind of, for each cell, we can store a sum for each like diagonal ID, and then over all the IDs we can take the maximum sum. The problem is we have negative values. However, because the column is at most n minus 1, therefore the whole value can be at most, or can be like at worst negative n minus 1. So if we add n minus 1 to this, then these values are now guaranteed to be positive. And they'll specifically be within the range 0, 2, n minus 1, where they were initially in the range negative n minus 1, and then positive n minus 1. And then we add n minus 1 to that, so it's just like interval stuff. The whole interval shifts by n minus 1. But anyway, that's another way to do it. You can keep an array that represents the sum of each diagonal ID. For each element, you increment its sum in its like respective diagonal, and you take the maximum over all diagonals. That is another possibility. Let's do combination lock, and this one I found absolutely terrible. I had a lot of trouble with it. Maybe it was easier than I thought, but I don't even know, man. It just kind of sucked. So here's my idea. We can represent, consider the cost function, like, define like c of xy to be the cost from going from x to y in the combination lock. Okay. Now there are three possibilities. We can go directly, as in not using the properties of the combination lock and not like going from 1 to n or n to 1. We can kind of like underflow and go below and then immediately like jump up to n, like from 1 to n, just because of how the combination lock works. So we can go under, and in the same manner we can go over. These three all have their separate costs, and we want the minimum of all of them. So for this one, it's x minus y. Now say we go under, which means we have this line here, we have this point y here that we want to get to, and we have this, wait, that doesn't make sense. We have this point y here that we want to get to, and then we have this point x that we are coming from. Now, the path we're going to take is going to kind of go like this. We go here, we jump over, and then we go here. But this is the same as kind of like, just like shifting this point over by n, or k. I keep calling it n, but it should be k. If I say n, I mean k, and I'm sorry for that. Alright, what do they do? Okay, I've been doing this right the whole time. So, okay. Sorry. N is the size of the combination lock, and there are W wheels. I probably should have like done that in my own code. In my own code, I used N and K, where N is the number of wheels and K is the size of the combination lock, which was very confusing, to be honest. And I don't recommend doing that I don't recommend doing that. So now we're going to use the right terminology and say N is the size of the combination lock. So then this is essentially saying we shift X over by N, and then just kind of like go to the left. It's the same path, we just kind of like overlook the skipping part. And it works out. Yeah, so in a similar manner, when we go from the right to the left, it's the same thing as shifting it over by n to the left, and then we have this new point x, and then we take this path going over here, and this is of size n. So essentially, this is, if we go under, we shift it n to the right, and therefore it's the distance between x plus n and y. If we go over, we shift it to the left, and therefore it's x minus n. It should be minus y, that absolute difference. Because this absolute difference is just like the distance. So that's cool. And then the cost c of xy is the minimum over all of these. Okay, why is this useful? Because let's like do out a case now. Let's say this is what I used before. Actually, we'll do n equals 8 because that's more convenient. So say we have x here, and we're trying to, like, the whole point of the problem is we have to find a certain value of y. So let's say we have y. Let's just consider what all the values of y here. So say we wanted this to be y. Then the best move is to go 2 over going this way, or like going this way and then going this way. So we can go 2 over, and so this cost is 2. This costs the same thing, we want to go around, so we get 3. This cost, it doesn't matter what we do, we get 4. This cost, we want to go this way now because it's better, so we have 3. We have 2, 1, 0, and 1. So notice here how it's first increasing, then decreasing, then increasing again. So let's kind of consider this function that we get, this function c of xy for a fixed value of x. Because we fixed the value of x for a specific ai, that's the starting point. So here it's going to be like this. Let's do it like this. And then it's going to start decreasing to 0, and then it's going to increase again. So like, because these points are kind of intermediary, all we're really interested in is the points where the slope changes. So the only things we need to check are here, 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 and here. Because say the slope is decreasing, then any point here is going to be like overshadowed by this point. This point's just going to be better because when we go later on, the slope's going to be better. And even if the slope is increasing, then we'll already have checked before, and therefore this point is automatically going to be higher than this point. So there's no point in checking that. All we really care about are the points where the slope changes, or the beginning and the end. It's kind of like intro level calculus, kind of, the way this kind of analysis works. Okay, now the problem is this alone is one function. What we have is a lot of functions because there are n different there are w different values of x, and we need to consider all of them. So maybe we have some different function that goes like this. We have something like that, and then like that, and then like that, and then like say it overlaps here actually. That, and then like that. So we have different points where this is a beginning, then this is a beginning, this is a point, this is a point, and this is a point. And so this aligns with this aligns with this aligns with this aligns with this, and this aligns with this. So we have even more interesting points. Right, so now the sum of these two functions, we have to consider 7 points now. Yeah, that's even more fun. And then we can just, we can just like keep sticking on more and more functions. But like, the idea is there aren't going to be that many interesting points. Here's the idea. So this will dominate for a certain range, and then at some point maybe it will change to this one, and then at some point maybe it will change to this one. But like, all of these have their own ranges which they dominate, and then they stop dominating. Okay. Basically, there aren't going to be that many points that we care about. Specifically, maybe this will have this will be the endpoints. So this will take 2 points maybe, or just there'll be 2 on the end. And then at some point this may start dominating, so there's an extra one, and this may start dominating, so there's an extra one. So we have around like 4 points. Maybe not exactly, maybe less, maybe more, but we have around 4 points. So in total we have 4n interesting points, and we don't count the n's multiple times, so it's even less than that. But in total we only have O of n interesting points. So now we just have to figure out how to do this function. Okay. Now here's the cool part. I think this is like called slope trick or something, but it's like, it's kind of just like, basically to add functions, what you can do is, say we want to find the added function at this point, which just happens to be here. No, it's like way above, but whatever, right? So the initial point of the added function is the sum of these two. And then the amount it changes from here to here is going to be the slope of this one plus the slope of this one. So really, at any interesting point, there are only 2 values we need to keep track of. We need to keep track of its actual coordinate, let's call it v for value, and then m for slope. And then between this interesting point and the next one, it's going to change by, let this be x1 and let this be x2. Then it's going to change by x2 minus x1 times the slope. That's just like how it works, because at each point we're going to go up by m, and we're going to go up x2 minus x1 times, so that's the formula. So if we somehow had the values and the slopes at all of the interesting points, and actually we don't even need the values at all we need really are the slopes. And I realize I kind of overcomplicated it myself, but all we need are the values and then the slopes. Or all we need is the initial value, sorry. So that is the cost, say, when we start at 0, which is this one. And then we just need the slopes. So when we get here, the slope changes from +1 to -1. So this would be a net decrease in -2 of the slope. But like, it's still like the same added function we have. So here, we just kind of like model this change in slope by decreasing 2 from the overall thing. And then when we go over the whole function, we just start at our initial point, and then we go along and we take this formula for each like consecutive pair of interesting points. So here we would find the sum of the function here, and then we would go to this interesting point and take this again, because that's how much we changed since this point. And then we go here and we find this interesting point by also finding how much we changed. And then we do this for all interesting points. And again, an interesting point is one where the slope changes. I may have not made that clear. But like, that's just it. We looked at all interesting points and we computed their values only combining the slopes. And obviously you can add slopes together because it's just how like functions work. So that's it. So now it remains to figure out how to actually find what these functions are, because this is kind of convoluted. So let's like figure out the point where like these two become equal, because like kind of like, I'm not sure if it's calculus or whatnot, but there's some like, it just kind of makes sense that like if this is increasing and this is decreasing, say, then the point where they intersect is going to be the point where this one starts being better than this one. Right? So we just need to find the point where they intersect, and then we can find how the function changes. So let's just like solve for it, man. So we have x minus y is equal to x plus n minus y. So like by definition, x plus n is greater than y. So we can drop this absolute value and say we have x plus n minus y. And this is equivalent to, again, shifting over this way and then going that way, which is shifting by n, and then going this way. Okay, but like the only reason we would need to shift by n to the right is if we're not already enough to the right. Like say we were to the right of x, why would we ever need to go more to the right? We wouldn't. So we only use this value when the y we're considering is less than x. So now we can assume y is less than x, or less than or equal to, I guess, but basically y is less than x. So therefore, wait, that's not right, is it? No, I'm kind of confusing myself. This should be y. Sorry, y I guess is the ending point, and then x is the starting point, and then we shift x over by n, for example, here. That makes more sense. So then we assume that x is less than y, which, yeah, otherwise the whole thing will like kind of cancel out and we get 0 equals n, which doesn't make sense. So because x is less than y minus x is going to be the positive one. So we get y minus x equals x plus n minus y. Solving this, we get 2y equals 2x plus n. And therefore, x equals y minus n over 2. So this is the point where these two functions intersect. If n over 2 is even, this point is at an integer, otherwise it's at a point between two other points. Which just kind of makes sense, right? Like we just go 4 over here, and then this, like both of them are 4. So yeah, it just kind of makes sense. And then similarly for going from directly to over, it's the same thing, but this is negative. So for over, we just have x equals y plus n over 2. The problem is with n is odd, then we kind of like don't have a discrete function. And we want it to be integers because that's convenient. So one way you can do it is just to multiply everything by 2. That's a possibility. Or you can be even weirder about it and just like add more interesting points. So for example, here this cost is 2, this is 3, this is 3, this is 2, this what? This is 2, this is 1, this is 0, and this is 1. So the point where this changes is here, which means you can kind of represent it as this segment, then this segment, then this segment, then this segment. I'm going to make that slope a bit more visible, and then this segment. Right, like even if the point isn't an integer, you can kind of just like bridge the gap by choosing the two integers between it. So let's like consider the bigger integer on this side of the gap. Then this is floor n over 2 because we want to subtract as little as possible. This would give us exactly this. We would subtract 3. And then the other value is that minus 1. And similarly, if we're on the left, then we want to go further, and therefore we want to go ceiling n over 2. And the other value is that minus 1. So really the only interesting points we have are 0, comma, y minus floor n over 2, or I guess it's ai. ai is the starting point. So the only interesting values we have are 0, ai minus floor n over 2, ai minus floor n over 2 minus 1 because we want both sides. And note that it doesn't matter if we have more points than necessary because it just like means we kind of know the function even better. So even if n is even and this point isn't necessary, we can still get away with having it. So for implementation purposes, it's just kind of easier to do this. Then we need ai itself because this is the point where, that's the point where this stops decreasing and then starts increasing again as you get farther from x to the right, or farther from y to the right. And then we also need the other one, ai plus the ceiling of n over 2, ai plus the ceiling of n over 2 plus 1, or sorry, minus 1, that's the other side, and then we can have n minus 1 too, because like it's just the endpoint. So we consider the starting point, the point where this becomes interesting, the point after this becomes interesting, the point where this becomes interesting. These are the points on the left, this is the value itself, these are the points on the right, and this is the right endpoint. But notice that like all of these values can't exist at once. Like if this value, and we also, like you don't want to add points that aren't within the range because that's kind of going to mess up the function. So we only really care about like at most one of these values. So even though there are 7 here and it seems like a lot, there are going to be fewer. Say for example 5 or something. Maybe it's in the middle, it'll have like 6, doesn't really matter. But the idea is like there aren't that many points. So say we have all the valid ones and we sort them. So we have, say for example, possible values of x, xo, x1, x2, x3. Then the slope is, then these values, the values of their functions are c, the cost of, what would it be? It doesn't, the order here doesn't matter because it's just like the same. So we have c of xo and ai, c of x1, ai, and so on. We just continue. So the slope between these 2 points is simply y minus y over x minus x, rise over run, which is, I'm going to draw it bigger now. So it's c of x, like for some j, it's c of xj plus 1 ai minus c of xj ai. Or again, ai is the fixed value that we're working with. This divided by xj plus 1 minus xj. This is the difference in y, this is the difference in x. This is the slope between these. And now we have all we need to construct this function. We have the interesting points, we have the slopes between them, and we have their function values themselves. It's just simply this, the minimum of these 3. So to combine the functions, we can kind of just like use a map where we store for each interesting point, or we really only need the beginning value here. So we store the beginning value, and then we store for each interesting point the sum of like the slopes that are applied to it. For example, this point has a slope of +1 and a slope of -1, so its total slope in the added function ends up being 0. This point has a slope of -1 going down, so the overall point has a slope of -1. This point has a slope of +1. This point has a slope of, or actually what happens here is the slope changes from +1 to -1. So in total, the slope decreases by 2. And then here, the slope changes from -1 to +1, so the slope increases by 2. Here, the slope decreases by 2. Here, it increases by 2 in both places. And here is the endpoint, so it doesn't matter. So we can kind of like, if you know what a map is, it basically maps integers to values. So we can map each interesting point to the sum of the slope changes that happen on it. So we map x values to slopes, and then we iterate through x in increasing order, 1 to n, or 0 to n minus 1. We iterate through only the interesting points, and then at each point we consider the formula of, what is it? It's like the slope change. It's x 2 minus x1 times the slope. And then we update the slope, and we just do this for the whole function. That is how my solution works. If any of that was confusing, you can also see my code. it kind of does the same thing. I'm not sure how clean it is, but it's like, basically the idea is you read in the numbers, whatever, make them 0 indexed, and then you just like consider all the points and you put them in a set so that they're unique. And then I put them in a vector just so I can like iterate through their indices. Then for each point, consider it. For each point, consider it, and also consider the next point, and then find the slope between them by computing their function values. Call it slope, and then I kind of overcomplicate it by also including the values. You don't exactly need to do that because you guarantee at each point the values are the same. So basically, literally the only thing I was doing was adding 0 every time. So there's really no point in doing that, right? So just don't. Like, ignore this value thing. All you need is the initial value. And then here you would update the slopes. At the beginning, it would gain this slope, and then at the end, it's kind of like a segment thing. At the beginning, you gain a slope of +1, and then at the end, this slope kind of runs out, so you lose that slope of +1, and you need to subtract 1. And then you have this new segment that kind of starts, and that has another slope of -1, so you would add another -1 to this point, which is where -2 comes from. And at this point, this segment of -1 ends, and so you would add +1 to cancel it out. So that's what I'm doing here in this. You begin by adding it, and then later cancel it out by subtracting it. And then finally, go over all the points. This is pointless, don't do this part. But basically, you just compute the differences, you maintain the last point, and then over all possible interesting points, take the minimum. And of course, print it. Okay, that took a long time, but it was very convoluted, in my opinion. I'm sure there's some other like big brain solution that I kind of just missed, which I would be sad about, because I saw people did it in like less than 10 minutes, which is very scary. But that was what I did. And then this one. This one I found simpler, because it's probability, right? So let's take some value like 19, 3, 78, 2, and 31. Okay, this is kind of confusing. I'm going to use single-digit numbers because otherwise it's kind of hard to read. So let's say we have 7, 3, 2, 5, 6. Same 5 numbers. The numbers actually end up not mattering that much, so we'll just kind of stick with it. And we want to figure out like the expected value of the merging. I'm kind of glossing over the problem statement. I think I also glossed over the problem statement in the last one, but like you can read it, it's fine. It's not, none of these statements are really that complicated. Actually, this one's kind of like, you kind of have to understand probability to get it. So basically, you start with 5 cards, or n cards, and then at one point, you pick a random consecutive pair uniformly randomly. And then you say that you're going to merge this pair together. And then, so this becomes a 5. Then you also gain a value of the, you also gain the value of the 2 cards, of the sum of the 2 cards that you merged. So if you create a card with sum 5, 3 plus 2, then you also gain 5 as a bonus. And then here, say you merge these two. Actually, say you merge these two. No, let's do these two. Then you have 11, and you gain 11. Then if you merge these two, you have 12 now, so you gain 12. And then, you know, same thing, 23. You just merge these two. Right? Okay, and then the total answer is the sum of all the values you just got. Cool. Now, the problem is the randomness. And basically, you don't want to figure out the value for a specific thing. Given that all merges have equal probability of happening, you want to figure out the expected value of the final value you get, the sum of each value for merging. And the expected value being over all possible things. Okay. Let's consider just some arbitrary sequence of merges, right? And then we'll say, what we want to do is we want to track a specific element. And like, what happens to this element? So say we go here. Then this 2 becomes part of this. And then so it gets added in this. So we get plus 2, and then we get something else. And then when we get here, this 2 is a part of this element, which means that it's also going to be added into this interval when we do this merge. So we get another plus 2. And then here, we get this 2 gets added again because it gets merged into the huge interval. So in total, we merged the 2 3 times, and therefore the value we got is 2 times 3 from this specific 2. And notice that we can do this for all elements. So for some specific sequence of merges, this technique is called contribution to the sum, where you basically ask, instead of doing the whole thing at once, you ask for each element, how much do you get from that element alone? And then you can sum that up over all elements, and then that would be your answer. So for some specific sequence of merges, it would be just that. We figure out how many merges 2 participates in, or some element that was merged with 2. So this element has the 2 in it, so does this one, so does this one. So this 2 participates in 3 merges, and therefore we get 3 times 2 to the total value. This 3 also participates in 3 merges. This 5 participates in 3, the 6 participates in 3, and the 7 participates in 1. So for this sequence of merges, the sum of these 5 values would be our answer. Okay, now this becomes easier now, because now instead of caring about only the, how did you get the, actually I'm kind of interested, how did you get the second subtask? What was the second subtask? It was 100. How did you get that but not the third one? Maybe some n cubed thing or something? Okay, but right, so now instead of figuring out the expected total value of the game, all we need to figure out is the expected number of merges that this element participates in. And because of this cool thing called linearity of expectation, we can compute these independently even if they aren't actually independent. And then we can take the sum over all of them. I'm not going to go into how linearity of expectation works. I will, there's a cool blog by Brilliant on it, I think, so I'll leave that in the description if you want to like learn more about this kind of thing. But essentially it's just a bunch of probability theory like stacked onto itself. Right, so by linearity of expectation, we can compute all these values separately and then add them all together at the end. So now, for a specific element, what's the number of merges it participates in? Let's reconstruct the array. Here, I'll leave that visual up because it could be useful. 7, 3, 2, 5, 6. Okay. Now, let's focus on the 2 because why not? 2 is nice. It's nice, the only even prime number. It's got some like cool facts to it. Well, it's not that relevant. So, how many merges is this 2 going to participate in? Well, like, what's the probability of the first merge having 2 in it? So we have 4 possible merges. This one, this one, this one, and this one. And only 2 of these, the ones where 2 is directly adjacent, have this as a possible merge. So we have a 2 and 4. So we have 2, there are 2 outcomes out of 4, which give us a merge, so we have a probability of 2/4. Now let's say we do a merge. Maybe we don't include 2. Maybe we do. It doesn't really matter. But now we have 4 elements. So we still have 2 elements to the left and right of 2, but now we only have 3 possible merges. So there are 2 outcomes out of 3 where we merge 2, and therefore it's 2/3. Then say we merge 2 into this one. Now we get this. So now we don't have anything on 1's right, or 2's right, which means we can only merge on the left. There's nothing for us to merge with on the right. And therefore there's 1 outcome out of 2 possible ones, so we get a 1/2 probability. So like in terms of expected value, it would kind of just be summing all these probabilities up. But the problem is that like the probability changes based on which element you remove. Okay. Now, at this point, I actually read the constraints, and then I realized n is 5,000, and we can do this in O of n squared. So that's like a good thing, because for O of n squared, we can do this. This now becomes a dynamic programming problem. Let dp of a and b, come on, be the expected number of merges that contain this element. Expected number of merges specifically with this element, where you have A elements to the left and B elements to the right. So for example, this will be 1 and this will be 3, and we have, oh wait, no, this should be 2 and this will be also 2. Now, how do we compute this? Because like, imagine we had all these values. We just had dp for everything. Then the expected number of merges that have 2 in it is just literally dp of 2 and 2. So once we have this dp, the answer is simple. It's the sum of ai itself times the expected number of merges it has, which is, if we zero index I equals 0 up to n minus 1, then we get dp of I, because we have I elements on the left. For example, consider this index. This is index 1. We have 1 to the left and 3 to the right. So we have dpi, and it's going to be n minus 1 minus I. I'm not going to do the parens. This being because this is m minus 1, and we're interested in its distance to I, which is just like this subtraction. And similarly, we're interested in the distance from I to 0, which is just I minus 0, which is I. And that's the number of elements we have on the left and the right. So this is the answer. Yay! How do we do dp? Because once we have this, everything will be simple. Let's draw some sun around it. I don't know. Sunshine, yay. Why not? So to compute this dp, what we need is to figure out what happens. What are the transitions? Well, if we have A elements on the left and B to the right, if A is greater than 0, let's consider this structure, right? I'm going to get rid of this because it's kind of distracting. Just like delete the whole thing and then redraw the numbers, because whatever. 7, 3, 2, 5, 6, I think it was. Yeah. So let's consider this too. This is what we're interested in. If we have at least one element on the left, then we can merge with the left. So note that first of all, the probability of any one merge is A plus B, because the total number of elements we have is A plus B plus 1, and therefore we have A plus B plus 1 minus 1 pairs, like consecutive pairs, because only the first, like n minus 1, have something to merge with, and therefore it just comes out to A plus B. So there are, in total, A plus B possible merges to make. So the probability of any specific merge happening is 1 over A plus B. So if we have something on the left, therefore A is greater than 0, then we can add 1 over A plus B times, this is the probability of this merge happening. So we add 1 because this is a merge we get. Like, we add 1 because doing this adds a merge to our count. So we have a probability of adding this merge, and then whatever we get like remaining, it's dp of A minus 1 and B. So in the same regard, if B is greater than 0, it's 1 over A plus B times 1 plus dp of A and B minus 1. If we have more than one element to the right, or to the left, say, then we also have some of these merges that don't include 2. Specifically, we have A minus 1 of them. Because note that we have A elements to the left. This whole array is of size A, and by the same argument, there are A minus 1 elements that can be merged. But this is only possible if there's more than one element to the left. Because otherwise, any merge would include this one. So if A is greater than 1, then no, A is greater than 1, then we could have, there are A minus 1 possible merges divided by A plus B times, we don't get the 1 here because this specifically doesn't add a merge. So it's just dp A minus 1 and B. Because we still remove an element from the left. And, come on. Once again, if B is greater than 1, just like the same analogy, B minus 1 over A plus B times dp of A and B minus 1. Cool, this is it. These are the transitions, because either we merge with this one or we don't on both left and right, and that's it. So notice how these already like sum up to A plus B, which is cool. If A is 0, we'll just like ignore these, so no matter what, it works. And the answer is the sum over all of these 4. And if this isn't like anything, then it's just 0. Like if A is equal to 0, for example, then we would take 0 for this one and this one. The base case is simple, where we have nothing on the left and nothing on the right. So obviously there's nothing we can do, and therefore we just set it to 0. So that is it. Those are the transitions. Again, we either directly merge with the 2 on the left, merge on the right, merge with something other than the 2 on the left, or merge with something other than the 2 on the right. And then once again, the answer is this sun-encased expression, which is AI times dp of I and m minus 1 minus I. And that's the answer. Be careful with doubles. Be sure to do something like set precision, otherwise you might you want to print many digits. So what I did was set precision, like for example 10, that would print 10 things after the decimal point, or maybe not, like some number after the decimal point. And then you just sum that up. And so in the code, this is very simple. Compute the probability. Then if I is greater than 0, if j is greater than 0, you just literally do out all the transitions. And then sum them up. So this dp is O of n squared in total because there are only 4 transitions, and therefore the whole thing is O of n squared, because this sum only takes O of n to compute, since you can pre-compute dp beforehand. So yeah, that is Kickstart. This is pretty enjoyable. It was better than last time. Round F was kind of sketchy. Wasn't really the biggest fan of the problems, but this is pretty cool. So, I don't know, what do you guys think? Should I actually try to, get a very, very good rank on one of these rounds? For example, I kind of held myself back by, I explained almost everything before I even wrote the code, which, in terms of commentary, is a good thing, but in terms of getting a high rank and, clickbait whatnot, it's not the best thing. So, it's kind of a trade-off. What do you think? Should I try to get a really good rank in rounds, or should I continue with this level of commentary while solving the problems and kind of the thought process and stuff? You can I don't know, leave a comment, something, whatever. Yeah, because I'm not really sure myself. Use this as a thumbnail, something show somehow that I solved all the problems. That's all I need to do. Alright, that's all I got. Hope you enjoyed, and goodbye.